Hello everyone, welcome to A plus BI. This channel is all about complex numbers, and in this video we're going to be solving a very interesting polynomial equation with complex numbers. Why with complex numbers? Because a polynomial of degree n has n complex solutions. Of course, complex numbers include the real numbers, which is interesting, or you can also call them an extension. Anyways, we have this interesting equation, and the reason why I call that interesting is, I think super interesting, is it's missing some powers. Take a look. We don't have z to the fourth, we don't have z squared. So what is going on here, right? Really a crazy scenario. And why is that important? Let me tell you. Suppose you had the full equation z to the sixth plus z to the fifth plus z to the fourth plus z to the third plus z squared plus z plus 1. I know that's going to be a long equation, but if you had that and just add 1 to both sides for the time being, or just consider the fact that, okay, fine, this can also work. Well, maybe not. Anyways, let's just add 1 here for simplicity's sake. If you had an equation like this where you had all the powers, right, you could solve it easily. Why? Because when you set it equal to 0, let's just say this is equal to 0 for now, you could just notice the fact that, hey, this comes from the seventh roots of unity. What is that supposed to mean? Well, if you're new to complex numbers, go ahead and check out my lecture videos. I also have another channel called Cyber Math, that is cyber with an S. So go ahead and check it out and let me know what you think. But back to the equation. If we had all these powers, we could easily multiply both sides by z minus 1. And of course, on the right-hand side, nothing is going to change. The left-hand side would be z to the 7th minus 1 equals 0. And from here, you could safely say that, z is basically 7th roots of unity, 1. Except for 1, of course. In this case, we know that z cannot equal 1 because z equals 1 does not satisfy the original equation. You know what I'm talking about? I hope you do. But you could also use the sum of a geometric series to come up with that. No matter what you do, you're going to come up with the same thing. So, what is going on here? Well, we have all the powers, everything looks good. And you can look at smaller versions of this problem, like maybe this one, or even this one, or even this one, right? Remember, this expression comes up a lot in cube roots of unity, right? But we don't have that. Unfortunately, too bad. Houston, we have a problem. So let's go ahead and solve this problem. How can we figure it out? Because we're missing some of the powers, we're not going to be able to use that method, obviously. We're going to use something else. And this is where certain tricks are important. You need to know algebra. If you're going to be solving a polynomial equation, an algebraic equation, you need to know tricks of algebra. Maybe one day I'll write a book and call it The Tricks of Algebra. Who knows, right? Should I do that? What do you think? Anyways, so let's go ahead and take a look at it from another perspective. Now, if you look at the last 3 terms on the left-hand side, they go down by 1, right? I mean by 2. That's what I meant. This is z to the first. So they're odd powers. In that sense, they're kind of kindly separated from z to the sixth. What do I mean by that? So, for example, if you just focus on the last 3 and factor out a z because they have a common factor, you would get z to the fourth plus z squared plus 1. Now, this should be a clue for you. The reason why I show you these things is so that you can recognize these patterns, okay? What do you notice? Well, if you set z squared equal to w, the expression inside the parentheses gives you w squared plus w plus 1. What is that supposed to mean? Again, this is the cube roots of unity. Why? You can multiply by w minus 1, set it equal to 0, and exclude 1 from this equation. Or you could just solve it as a quadratic. You would get something like a negative 1 plus minus root 3i over 2. I memorized it. So on and so forth, right? So, again, there's a lot of hidden treasures here. But what about the z to the sixth, right? It's, again, weirdly separated. Here's the thing that we can do. We can actually do something about it because we also have a 1 on the right-hand side. This is not equal to 0. That's another problem we have to deal with. So here's what we're going to do. We're going to subtract 1 from both sides, and that makes a lot of sense because that'll eliminate the 1 on the right-hand side. So here's how it goes. Oops. Here's how it goes. You start with z to the 6 and subtract 1 and then continue with the rest. You know what's going to happen, right? And on the right hand side you have a 0, which is beautiful. Awesome. Great. Now here's where the separation comes in. We're going to focus on this and on this, and we'll do that separately. And what is z to the 6th minus 1? Let's think about it. Difference of 6 powers, or difference of squares, or difference of cubes, however you want to look at it. But for the purposes of this video, I'm going to look at it as difference of 2 cubes. You know why? Because it gives us the powers we're looking for. Let me show you. So we're going to write this as z squared cubed minus 1, and it's factored as follows. Remember a cubed minus b cubed? Hopefully you know that. A minus b, right? A squared, this is a by the way, plus ab, which is z squared, plus 1. Beautiful. Exactly what we got here, right? Remember that? When we factored out the z. So what's going to happen next? We're going to factor the z out, and we'll proceed with the rest. And that's going to be super duper easy. So allow me to write these two factors here. Okay, z to the 4th, z squared, and 1, plus z multiplied by z to the 4th plus z squared plus 1. This is the beauty of algebra. See how beautiful that is? You do something, and then it just works out. Now, what are we going to do? The rest is easy. We're going to go ahead and factor out z to the 4th plus z squared plus 1, which is easy to solve, by the way. Multiply by this plus that. Let's go ahead and put it in the standard form, right? Be a good student and write it in standard form. There you go. It's all factored, and if you don't believe that, go ahead and distribute and simplify. You'll get the same thing. Of course, this assumes that you subtracted 1 from both sides in the first place, but even if you didn't, you should. Okay, great. Now, let's go ahead and solve this and find the solutions. Now, you can start with either one, but this one is quadratic, so let's start with that. By the way, this has nothing to do with the cube roots of unity or cube roots of -1. It's totally a different thing, which I think is amazing because you'll be surprised at the results if you haven't recognized what I'm talking about. Okay, z is equal to -1 plus minus the square root of b squared minus 4ac, which is 5, divided by 2. Did you recognize it? Some golden ratio flavor, maybe? Right? So those are the z values, and guess what? These are real z values. Okay, let's go ahead and look at the non-real ones. Wait a minute, are they non-real? Of course they are not. So now, again, I'm going to leave it up to you to solve this problem because this is a quartic. It has 4 solutions, so you can kind of use the same trick that we used before. Multiply by z squared minus 1, and you'll still get 0, but this will give you z to the 6th power minus 1 equals 0, or z to the 6 equals 1. In other words, but this time you have to be careful because this is the extraneous factor that I introduced. So you have to make sure z squared minus 1 does not equal 0. In other words, z does not equal plus minus 1. We have to exclude 2 values from here. So we're going to be looking at the 6 roots of 1. Those are going to be solutions. If you write 1 as e to the power 2 pi n I, from here you're going to realize z can be written as e to the power pi n I divided by 3. N equals 0 gives you 1. You don't want that. N equals 6 gives you 1 again. You don't want that anyways. And n equals 3 gives you, so n does not equal 0, n does not equal 3. You can use everything else. For example, if n is equal to 1, we're going to get z equals e to the power pi I, or I pi over 3. And you should know that from Euler's formula, because Euler is the best, e to the I theta is cosine theta plus I sine theta. And I go over these things in the lecture videos, by the way. Make sure to check it out. This is cosine pi over 3 plus I times sine pi over 3. I'm not going to show you all the solutions because that's going to be a lot, but you can do this for yourselves. As long as n does not equal those values, it can be 1, 2, 4, and 5. That's it. You only get 4 solutions because it's a quartic. Yay. And cosine pi over 3 is cosine 60, which is the same as sine 30, which is 1/2, plus I times root 3 over 2 will be another complex solution. And of course, we have these real solutions as well. Together, we have 6 solutions because this is a hectic equation. And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care. Don't forget to check out Cyber Math and aplusbi, and bye-bye.